Hi. So the Nmr Pulse sequences are one of the most elusive things when it comes to the NMR. It's incredibly complicated to visualize. So I wanted to, if we were on campus, I'd take you downstairs and we would play with some pulse sequences, and you would get some spectra, and then you'd be like, oh, okay, I think I can understand the connections. So I'm going to try and recreate that. Welcome to Virtual NMR Day. Okay. So first of all, let's talk about pulse sequences. If we went down to the NMR and we did a simple proton experiment, it would probably look something like this. So you've got some sort of initial delay. I tell you, but I have to sneeze. Sorry. I'm good. Okay, so there's a delay. This would be pulse 1. This would be delay 2 after pulse 1. Notice that both of these numbers are 0. So essentially you have a 3 microsecond delay and then a 7.9, probably a millisecond pulse width. So the width of the pulse is this time right here. And then you have your signal. And so this would be the decay that you would be monitoring. Okay, so this is a very simple pulse sequence, and that pulse sequence comes from the radio frequency of the the input. So once the spins are in alignment with the magnetic field, and they're all going in about their own basically equilibrium states, then you're going to pulse it and rearrange the direction of those pulses, or rearrange the direction of those magnetic moments, and then watch them decay. So you flick them out of equilibrium and you watch them decay. Go team. A little bit more complicated than that. So I'm going to show you a pulse sequence, and this is a spin echo that you would get from a pulse sequence. Okay. This is from the Wikipedia page on spin echo, and this is a fantastic animation. So I want you just to watch it for a second. And I've got other videos on YouTube, or on Moodle via YouTube, posted to help explain some of these ideas, but I wanted to help kind of bring you through it. So the 90-degree pulse. So first of all, this red thing is the magnetization vector. So this is the Z0 magnetic moment that is being projected onto the Z-axis. And so in this case, it's so it starts up. So it's starting in the up direction, and then you can imagine as this is the X direction, this is the Z direction. So we put it out of alignment, so it's a 90-degree pulse, and so it flips. 180-degree pulse is going to flip around, and then the dephasing is going to occur. But as the X component disappears, watch what happens to my pointer. The Z direction comes back, such that it's going to, as the X direction disappears, the Z component is going to reemerge. And we are watching the disappearance of the X component, or we're watching the appearance of the Z component. Cool, and that's the spin echo. Sweet. So this, if there's only one T2 relaxation, then if there's only one nucleus, let's just say it's all pure methane, liquid methane, that's dumb. Let's assume that it's all pure one possible frequency. So it's like octane, why not? And the majority of the protons are CH2. And so you'd have one frequency decaying, okay? And that is called the FID, the free induction decay. So we're watching that free induction decay caused by the echo of this magnetic moment disappearing. Cool. Okay, I'm going to pause for a second and grab my other slide. Oh, nope, that's pause recording. There we go. Welcome back. So here you have basically that picture, but just not animated. This is one of the reasons I don't even have lecture notes for the pulse sequences. I just throw the animations up on the screen and we just watch them for an hour. But now there's YouTube. Oh my God, I'll be using YouTube in the future. So 90-degree pulse, dephasing occurs, 180-degree pulse, it flips them over. Then you have the disappearance of the main vector, and it's that disappearance of the Z-axis growing that you have the induction decay. Okay, so here you have 90-degree pulse, free induction decay, 180-degree pulse, then you have your echo. So sorry, I should have clarified. So the spin echo is going to be the response of the dephasing after you've done the 180-degree pulse. So technically you would have, if you just had the 90-degree pulse, you'd have a free induction decay already occurring. So that's this dephasing here, because as it goes around, these things are going to slowly spiral back up. And so for a simple 90-degree pulse with nothing else, then you're just going to have free induction decay afterwards, which is what this is representing, or sorry, this first half is representing. Then you do your 180-degree pulse, you have your spin echo, because now you've got these spins that are coming back together. So this is kind of I don't know why it's called an echo. I should look into that. But that's why you don't have a complete like attenuation. You have an increase and then a decrease again, because these are getting farther apart and then coming back together. Whereas here they were all coming back together until the 180-degree pulse. Okay. Hope I didn't confuse you on that one. The other thing I wanted to share about this is that your relaxation times are going to be unique to the different specific nuclear environments. So if you have multiple things that have the same nuclear environment, they should have the same relaxation. Okay. What's next? Oops. Okay. So here you have a simple 90-degree pulse. And so 90-degree pulse, it goes down like that, and then it goes back. So it relaxes back. If there's only one possible relaxation rate, then you're going to have a free induction decay that looks something like this, and then that's going to yield one frequency. So here is your Nmr chemical shift. If you have two nuclei, you're going to have a free induction decay that looks something like this, and you can actually see there's 1, 2, 3. That's the lower frequency one, so that would be here, and then you've got kind of the more rigidy one, and so that would be the smaller frequency. And so then you're going to have a lot higher, like multiple peaks. So you have multiple nuclei here, resulting in multiple peaks or multiple Larmor frequencies. Okay. Cool. Hope that helps. The difference between, so this is a time dependent. This is your function f of t. This is f of nu, the frequency. So to get from this to this, you do a Fourier transform. Cool, which I think Deanna took you through that in instrumental analysis. So hopefully you had that class. If not, and you're interested, shout out and then we'll have a FTI, a Fourier transform chat. Atkins goes into it a little bit, but basically just know that it changes the domain. So you go from a time domain as this is a function of time, to a frequency domain as this is a function of frequency. Okay. Cool, so here's a very simple proton pulse sequence, just like the one that I showed you on the VJ-NMR software that you would have on campus. Pulse sequences can get very, very, very complicated. So here are a few. So this would be your delay time, that pulse, your spins have flipped, and then you measure your single. This is called the acquisition time. Okay, here are several types. So there's proton, you've got 90, 180, 90. You got a long decay to collect quite a bit of data and let all the nuclei kind of reestablish themselves. And then you've got another 90-degree pulse, and then you've got a series of 45, 90, 180, 180, 90, 45. That's too cool, oh my gosh. Nitrogen 15, you've got several different types of pulse sequences. Carbon 13, also, here's some of the stuff that I've done before. So this is pulse field gradient. So now you're changing the gradient of the magnetic field. So B0 is no longer constant across the entire cell or your NMR tube. Now you're changing the strength of the magnetic field as you're changing the pulse sequences. Holy goodness, there are so many different complicated techniques that you can do with NMR. And it's really about controlling what the spin states. Actually, I'm going to stop share there. It's all about controlling the spin states when you've got nuclei going in one particular direction or in another, or I should say the magnetic spins of those nuclei going in one particular direction or another. So back to this picture, and I should add that the YouTube video that I set the link to is showing a step-by-step visualization of a very complicated pulse sequence, but in the discussion, I think it helps to talk about the laboratory reference frame and then the nuclear reference frame. If you want to visualize this, and I'll designate that video as optional, but especially for my synthetic chemists, knowing the NMR beyond just characterization is a really important thing. Okay, so it's all about controlling the precession of those magnetic moments. So we know that they're processing at the Larmor frequency, but if we can control via multiple spin flips and directions, we can basically talk to the molecule's nuclear spins in very unique ways. And from that, we can get a better understanding of the unique individual or the unique molecular or nuclear environments. Go team. Hope that helps. NMR Pulse Sequences, it takes PhD to understand them. It's insane. But having an appreciation for kind of what they do with respect to the magnetic moment, I think is helpful. And yeah, those are definitely the things that you learn as you go. There are books and books on the different types of pulse sequences that you can do. They have fun names. When I was doing solid state NMR, there was one called REDOR, which I can't remember what it stands for, and I would normally grab my book off my shelf to figure it out. But there was a trap door, there was a back door, there was, I want to say there was a front door as well. There's so many doors when it comes to solid state NMR, but each pulse sequence was named. Cool. Okay, email if you have questions. That's all I got. I'll post those videos for you, and I'll deem them optional, but again, it helps just to visualize. So, go team. Bye.